Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
So I'm curious to ask you firstly, when you were a PhD student, you have been working in airborne computers for Howard Hughes aircraft.
Oh, yeah, way back.
And you mentioned that inspired you. So I'm curious about this experience to do a PhD and working in airborne computer for Howard Hughes aircraft. What kind of maybe shaped your way of thinking about computers at that time?
Well, I think the main thing is I had primarily been studied software, and I think that's what I expected to do because that was kind of my first love. I really, when I first took my first computer class, I tried programming and I was hooked. That's what I wanted to do. So I took hardware classes as part of the requirements of UCLA, but it wasn't the thing I was mainly working on. And then what happened, I was working as a research assistant on my PhD, and the contract ended and I needed a job. So that's why I started working at Hughes Aircraft. And so what we did at Hughes Aircraft is that we built computers that was to be airborne computers. And so then I got to learn not only just read about how to do hardware, but actually do it ourselves. And so I found I really enjoyed it. I think two exciting things if you're going to study computer science is designing your own programming language and designing your own computer. Those are both really fun things to do. And I think designing your own computer is a little bit more practical than designing a programming language. But so it was fun and educational. And then by the time I graduated and I went to Berkeley, I wasn't really sure which I was going to do next, more hardware or more software. And they really wanted somebody to do hardware. And so I happily took the job at Berkeley and did hardware.
So first of all, I would like to thank you for all the contribution I've been doing in RISC, because when I was a student, I have taken some courses in RISC and CISC, and I really fall in love with assembly language, how you go to the hardware level. The kind of thought that leads you to design RISC in that case, a reduced instruction set computer. Because when we studied that, for example, we started 10 years ago with a PIC, we student, and we tried to understand this kind of set. There's a specific set of instruction for this hardware. But I'm curious when you start to think about RISC in the design.
Yeah, so, this was done, it wasn't just me. There was also a lot of people at Berkeley, but there were also my friend John Hennessy at Stanford was doing the work, and then people at IBM were doing it. What had happened before the conventional way of designing instruction sets was to have this microcode interpreters. And so you could have very complicated instructions, and there was a way pretty economically to make it work. And the question we had was, well, you could design it that way, but maybe if we didn't have such complicated instructions, we could just execute it directly without this microcode interpreter inside. And so if you take that perspective, then you'd like to have a very minimal instruction set of not only not a lot of instructions, but also very simple instructions. And it turned out, once you did that, it also made it much easier to pipeline those instructions. So it was kind of a win-win in that you didn't have an interpreter and you could pipeline. And so that combination made it much more attractive than the microprocessors of the time. Like a factor of 4 better, maybe.
So why was controversial? Yeah,
it was very controversial because the perspective at the time is that software was and still is hard to do, and one argument that was made is that the high level of the software had to go down to low level assembly language, and that was not only a difficulty for building compilers, it was a difficulty for the software itself. And the claim was that's led to difficulties in software designs and led to these disasters where projects took forever. So that they thought of a higher level, a better architecture would make software projects go faster. That was the prevailing wisdom. And they called that high-level language computer architecture, that rather than aiming for assembly language, you'd aim for these high-level languages and then it would have all these benefits. So that was the prevailing school of thought of designing computers. And so this is very contrarian to that. This is saying, well, that has nothing to do, the actual language that the machines execute has nothing to do with that. It's really what the issue is, because compilers work, and what matters is the cost and performance and the speed that you execute, because, kind of speed is a characteristic. Faster makes it easier to build software as well. So it was contrary to the prevailing wisdom, and so that led to there would be debates at conferences with people to argue these points.
And I'm curious about maybe the counterintuitive thing is that for design philosophy, because, for example, we studied the Harvard structure and von Neumann structures. So when it comes to the design of the architecture, how do you do that to design a structure for a computer?
Well, these days, you could. You're not starting from a clean slate, right? So you can look at existing designs and start from there. If you were starting from a clean slate, you'd start from the instruction set itself, and you'd look at the operations it provides, and you have to do memory transfers, you have to do integer operations. Depending on the instruction set, you may have to do floating point operations. So you'd start with the instruction set architecture and kind of lay out the blocks that you have to have. And then the art is figuring out the balance of the resources that you have available, the clock rate that you can run them at, and then typically what's the average time it takes to execute those instructions that you design. So that's kind of the balancing act, the clock rate, the amount of resources, and how long the instructions take to execute.
Mm-hmm. When it comes to maybe what's still missing, because you mentioned sometime about Moore's law, maybe still the number of transistors is decreasing. I don't know how do you see this kind of advances so far?
Yeah. So it's pretty clear that what Moore's law said, what Gordon Moore said in 1965, is unambiguous. He said, as I look forward, and you can look at a graph that he has along a scale, and every year it shows the number of transistors per chip doubling. And then he revisited it 10 years later, and he said, looking back, it actually did that. It doubled every year. And he said, I think it'll keep doubling every year for a while. Eventually, it's probably going to slow down to double every 2 years. I just reread the paper. Now, when I say the thing that Moore talked about is no longer true, so that Moore's prediction, which was true for an amazing 50 years, it is not accurate anymore, so it's the end of Moore's law, then so many people have embraced bragged about Moore's law, is they interpret that mean is that semiconductors will not get any better at all. They're frozen in time. So those are not, that's not the opposite. Doubling every 2 years, it no longer being true isn't the same as there's no progress. But that's widely how it's interpreted, and that's why people get mad about it. You can have arguments now about whether Moore's law is still correct, even though it's factually, you could look back, if you look back 6 years, if it doubled every 2 years, then it should be that the number of transistors per chip is 8 times what it was 6 years ago. That would be Moore's law, and that's not true. Now, so what's happening now is we're slowing down, and each generation is getting more expensive. Both the mass costs are going way up and the process wafer costs are going way up because it's very expensive as we get into these very narrow line widths. And the gains that you get per generation are getting smaller, and the generations are getting a little farther apart. So we're seeing kind of this plateauing of the benefits where things are getting minorly more expensive and a small amount better. But that doesn't mean it's over. It just means it's slowed way down from what we were used to. The problem is, certainly for the software industry, they were used to performance doubling every, say, 18 months, and so they could keep adding features and the processors would make their software run fast enough. So some of them are continuing assuming that's true, even though the hardware is not going to do that. So the choices are either they have to make software a lot more efficient to make it faster, or we'll have to do different type of computer architectures than we've done in the past.
Do you imagine what kind of other architecture do you think maybe could be explored in that case?
Yeah, so what the conventional wisdom is that while we can't make nobody has an idea that shows a general purpose microprocessor be a lot better than the current ones. You know, the so-called von Neumann design, and lots of caches and lots of cores and out-of-order execution. Those ideas are pretty powerful, and no one's, for general purpose computing, has come up with a better model yet. However, for special purpose areas, you can have big gains. And the one that I mentioned in the introduction for machine learning is an area where they can have very special purpose hardware that can run that a lot better than a standard CPU. And so that hardware, like they're called the tensor processing units, or TPUs. TPUs can't run a lot of other software well, but it can run machine learning, at least a factor of 10 better than CPUs can run them. So that's an example of what the future probably looks like, is areas that have accelerators, and these accelerators only do that one thing really well, and we'll probably have a collection of those accelerators is the only thing we know now to make progress over the next 5 or 10 years.
Wait, I don't know if you can comment about Dojo by Tesla AI. In Tesla AI Day, when they announced about the Dojo project.
Yeah, I just saw the announcement. So I own a Tesla car. I'm on my second Tesla car that I've owned. So I'm a big fan of Elon Musk, and he's a visionary. But he always overpromises what he can do by the time he can do it. So the announcement that was done today, they haven't actually assembled the whole computer. They got one section of it working, and they made the announcement. And they said how good it would be when we finish building it and putting it all together, and how great it's going to be. But it's an interesting design. It's hard to tell just from the description how good it is. One of the things that if you use my textbooks, you can know how important benchmarks are. So a few years ago, there were no benchmarks in machine learning. So I and my friends got involved in starting that effort, and it's really taken off. It's called MLPerf. It's a very popular benchmark. So one of the reasons we started it was exactly for situations like this. Somebody makes a claim, they've got this great new architecture, look how good it is, look at all these cool features. Well, okay, run the benchmarks and let's see what kind of number you get. And that's been the way in computer architecture we've settled these debates. If you run the benchmarks and yours is a lot better numbers than our numbers, then we kind of tip our hat, congratulations, and that's great. If it's just we make all these claims and without running the benchmarks, it's hard to take it very seriously. For right now, look, this looks interesting, seems promising, but until you run standard benchmarks, we don't know how to compare to see how interesting it is.
That's a good point. Maybe I'm curious to ask you, as in design philosophy, what kind of question do you think, based on what you mentioned, what kind of important question you should consider in that case? Maybe in the design and the performance. What's really critical?
Well, I think for computers, it's all kind of hasn't changed, right? What's the cost performance? I would say, based on my, now that I've been working at Google for several years, from a Google perspective, from the data center perspective, the cost is not the purchase price of the chip. It's not the performance per purchase type. They refer to it as the cost for total cost of ownership. So what that means is the cost of buying the chip, or if you make it yourself, the cost of making it yourself or buying it yourself. That's what's called the capital expenditure. But then there's the operational expenditure. So for as long the lifetime of that chip, how long does it last? 3, 4, 5, 6 years, some number like that. How much power does it draw? It's mostly power, but what would be the operational costs? So what you want to minimize or maximize is the performance divided by the cost, the total cost of ownership cost. And so if you're factoring in the total cost of ownership, then you care more about energy efficiency, for example, and what's the peak power that you have to provision, the so-called thermal design power. So the TDP, as well as the average power usage, matters over the lifetime of the chip, not just its purchase price.
I don't know if you can imagine it would be the area that maybe should be considered to push the capabilities of the, for example, RISC architecture, or maybe to have a fast computer. What can be the area you think we have to push for?
Well, yeah, I'd say for the RISC architecture, I think what's kind of happened is we've kind of stabilized on what we think instruction sets, what the best ideas instruction sets. There's pretty wide consensus about what are the features of a good instruction set. And I don't think they've changed a lot in the last 20, maybe 10, 15 years. I think that there's general consensus of what are good things to do in an instruction set design. So as a result of that, about 10 years ago at Berkeley, as part of the research projects, some of the faculty and students I was working with said, well, rather than try and use these old RISC architectures from the 1980s, which is when I was working on it, let's do it ourselves. Let's do a brand new, clean slate RISC instruction set that'll be a better foundation for us to do our research. So because we had done at Berkeley 4 generations of RISC architectures in the 1980s, they called this one RISC-V. And so we were using it ourselves happily, and then people at other places started using it. And what we realized about 5 years ago is there was a demand for an open architecture, not just for research, which is what we did, or for teaching, which is what we did it, but for actual production use. So starting in about 5 years ago, we we looked at the success of the open source software projects and followed their lead. So we created a foundation, and this foundation's job is to popularize RISC-V and to enhance RISC-V. The name of that foundation today is RISC-V International, and as of today, I just saw the data, there's 2,000 individuals who are in it. There's 200 corporations and about 100 universities that are all participating in RISC-V. And those 200 corporations, interestingly, are almost evenly spread in Asia, North America, and Europe. There's kind of like approximately one third in each area. So it's a worldwide phenomenon. One of the authors of the RISC-V architecture and Andrew Waterman and I wrote a book about it, and there's a book available to buy in English, but we've also got free translations in Chinese, Japanese, I think Spanish, and Portuguese, I think. So if your listeners are in other parts of the world and want to download a free book, you can go to I think it's riscbook.com, and you see the links to the various versions. But that's a good way to, if you're interested in what the RISC-V instruction set looks like. And so the argument isn't so much that RISC-V is a fantastic instruction set, although I think it is. I think it is really a good instruction set. The big deal is that it's an open instruction set, and that's a new and powerful idea. So this means, and once you unlock the instruction set, that means anybody in the world can build processors to that instruction set. Conventionally, historically, instruction sets are always proprietary, so somebody owned that, and then they controlled who could build the processors. So either they would stop you from building it, or you had to get a license from them. And so then that's there's a business advantages to that, but it kind of stifles innovation because nobody can try things. So now with RISC-V, anybody with a great idea can get a working hardware software stack and add whatever thing they want to investigate as part of that RISC-V, and you have a big software stack, and you have open source design, so there's implementations written in System Verilog or other languages that you can download it and modify to put in the value, whatever features you want. So this is a very exciting time in computer architecture because of the openness and the experimentation you can do.
Actually, I'm curious to ask you that point because I think you are one of professor, maybe in academia, you have impact outside, in real world application, and many people talk about that. For you, why didn't you have this kind of take the opportunity to go and establish your company? I read that you resist.
I'd say, why did I do a startup? I'd say I had some time I was fortunate to get a job offer at Berkeley before I'd finished my dissertation. So it's not that unusual. I'd say, well, I applied in June, but I'm not going to finish my PhD until December, so I'll start in January. But I had some time to think while I was trying to finish my PhD about what I cared about, what I wanted to do, and I read some books about people's reflecting on their careers and what they liked. And what I got out of one of those books, actually, I have the book right here. I'll show you. It's and the book is called Working here, and it's obviously a book that must be almost 50 years old because I read it when I finished my dissertation. And what I got out of that book was that people who worked with people felt really good about their careers when they look back. I am now at the position where I look back at my career. And so this included, educators or ministers or people who worked with people that felt pretty good about it. And the people who did technological things, even more they cared about not so much the technological things as the people they worked with, right? And now for the people who built things that lasted a long time, like if you worked on the Golden Gate Bridge or the Empire State Building, physical structures that last a long time, you could look back and feel good about it. But the technological things tend to be, come and go. They didn't stay, so that could be somewhat unsatisfactory. So I kind of went into, the next phase of my career thinking it was going to be the people I worked with that mattered. So to me, it was trying to be happy and trying to shape people's lives was my goal. So I had this, kind of little story when people said, well, why don't you start a company? It's like, well, that's not, it's really hard to start a company. I'm aiming for personal happiness and trying to shape people's lives. So startups weren't really part of what I was planning to do. Now, I think as I look back, it would have been okay. I could have taken a 2-year leave of absence and done a startup company. That would have been fine as part of a career. I didn't need to be so strict about my vision. I'm a professor. I'm not gonna. I have to be a professor. It would have been fine if I'd taken a couple of years off and tried a startup. Now, most startups don't make it. 90% of the startups don't make it. So just because I tried doesn't mean I'd be successful. But I think it would have been okay. But I'm very happy how my career turned out and the choices. And it was one of the things that I like telling stories that kind of, I don't know, maybe 15 years ago or so, or 20 years ago, is a person who I greatly respected. He'd been the dean of the college, is retiring. And he told me, Dave, as I reflect back on things, the things that really matter in my career is the people I worked with, not the things. And I thought, I knew that. I got that from this book, right? I knew that going in, right? So he confirmed the same thing. And of course, now that I'm, let's see, I got my PhD in 1976. So I guess it's 45 years later. 45 years later, yep, it's the people you work with that are the things that are really the most important thing. So it's a long story about why I didn't do a startup. I think in retrospect now, it would have been okay. It would have been bad if I'd done a startup and left academia. That would have been really bad. And in fact, when Hennessy did his startup at MIPS, I was there rooting for him to return. Even though MIPS and I was consulting for Sun Microsystems and Spark, even though they're rivals, I knew John was a tremendous professor, and I, kept whispering in his ear that, as exciting as MIPS is, you're gonna want to go back to Stanford because that's best for you long term. And thank God, he didn't stay at MIPS because he became president of Stanford. I think the best president Stanford's ever had, and so it was really important for him to go back.
Thanks for sharing the story. Maybe you can go for the audience a question because we have a few questions. The first one, when do you think we will move beyond Newman architecture?
Yeah, I don't think it's going to happen. I was actually got to Scientific American for its 150th anniversary issue, which was in 1995, asked me to write an article about the future, about what microprocessors will look like in the future. And so I said, I'm going to predict for 2020. And what I said, and looking a lot of these predictions, is what people do when they write these predictions, is try to be entertaining, I think. And they say, look, this is going to be so fantastic in the future. It's going to be completely different. It's going to have all these really interesting ideas in them. So I said, I'm going to boldly predict that that's not going to be true. I said, I think the microprocessors of 2020 are going to be very familiar to the people of 1995. And I was right. Things haven't changed dramatically. I think the so-called von Neumann architecture, this idea you have a program counter and instructions, is a pretty, and you can modify software is modifiable. It's a very powerful idea, and there's a reason why things continue to look like that. So I don't see something radical coming on, at least for the next decade or so. I would think like the RISC-V work that we're working on. I think RISC-V is going to be popular for 10 or 20 years at least. I don't see something really changing dramatically. Now we can add accelerators, right? So if that's like running all the user interface stuff, a lot of software. But now special purpose accelerators that do things very differently, like the TPU has the systolic arrays. Now, doing something very novel for a piece of the program, that makes a lot of sense. But completely rejecting the von Neumann architecture, you can't find any remnants of that. That it completely disappears. I'll be very surprised if that happens.
And also the question about neuromorphic seems promising given how deep learning is working. I know there aren't great ways to train spiking neural nets yet, but we can just convert ANN to spiking neural nets in the meantime to run neuromorphic hardware.
Yeah, so neuromorphic, I think in general means inspired by the brain. And so that's just that certainly is driving the ML community. They are inspired by how the brain works. Now these spiking neural networks, it's like computer architecture, right? There are benchmarks in the ML community. They didn't used to have them, but they did adopt them, say, 10 or 15 years ago, and there are these competitions. Who can recognize the images the best? Who can do the translations the best? And so far, the people who are advocates of spiking neural networks have not submitted models to these competitions, because these competitions are kind of practical, right? They're things that you can imagine people like. I would like something that could identify what my camera sees, or I want these translations to be high quality. So anybody can enter these with any idea. And in fact, exactly what happened 9 years ago is for vision is somebody tried a deep learning model. Jeff Hinton and his students submitted to the standard competition a deep learning model, and they won and made a dramatic improvement in the quality score that first year. And that first year, they were the only one who tried that idea. And the second year, there was maybe 10 entries that were these deep neural networks, and 50 that were conventional. And 2 years later, 100% were deep learning. So that field completely turned to embrace the deep neural networking model because of success. So if spiking neural networks are a really great idea, the path is clear. Enter one of these competitions, do one of these challenges better than everybody else, and the field could change, right? But so far, they haven't demonstrated any. I'm not aware of any examples where spiking neural network has done well on any of these competitions. So it is a way to explore how the brain works. We'll do a spiking neural network because the brain probably does it that way. To understand the brain, that seems fine. But in terms of a practical alternative to deep neural networks, so far the proof's in the pudding, and they don't have the proof.
Yeah, and we have also another question, I think, to Good Day Captain. What do you think about postronic brains?
Yeah, I don't know anything about that. Sorry.
And also another question: when and if we can see RISC-V in consumer devices running complex operating system like one based on Linux?
That's already happening today. The problem for the RISC-V International is, because the RISC-V is most popular in embedded devices, you can buy the devices and you don't know what's inside. There's no bragging about that we're using RISC-V, but there's lots of products that are already using RISC-V. The two public examples are every Western digital disk drive, so that's like 1 billion a year, has RISC-V processors in them. And every NVIDIA GPU has RISC-V processors in them. There's watches that have RISC-V processors in them. There's cell phones with RISC-V. So we don't have a good way of, we haven't figured out how to advertise that, but there's our products today. And going forward, especially in the embedded space, RISC-V is very popular. So I would expect a lot of things that you use will have RISC-V in them.